Welcome back to our course on scanning electron ion probe microscopy in material characterization. We have been discussing on different surface properties using AFM. In our last lecture, we discussed on capillary force, electrostatic force and lateral force, atomic force microscope. In today's lecture, we will be discussing on chemical force microscopy, magnetic force microscopy and Kelvin probe microscopy. So, in addition to that, we will also talk on the conductive force microscopy or conductive AFM. If we look at the chemical force microscopy, certainly some kind of chemicals is involved here and a chemical force is measured. So, in order to measure the chemical force, we have a particular chemicals that we say functional group. It is attached to the surface of the tip and it can be also on the surface of the sample. And this force microscopy uses the chemical interaction between the tip and sample, and in this case the tip is functionalized with a particular group and then it brought close to the sample surface and made it to contact on the sample surface, and then it is pulled up measuring the adhesion force of those chemicals. So, as it done with chemical molecules or chemicals, so the resolution can be down to the single molecule. Irrespective of the morphology, wherever the chemicals are present on the surface of the sample, we can detect that, and thus it is also possible to pattern the chemicals on the surface. If we take a particular chemicals at the tip, then we can also do lithography type of studies that we will see in the later lecture, in the next lecture. But one of the important things that this chemical force microscopy should be carried out either in vacuum or in dry condition or under liquids in order to avoid the contribution of the capillary force, because capillary force can override the chemical force and thereby not providing the correct adhesion measurements or chemical force measurement. In particular, chemical force microscopy is used to measure the force of adhesion, the electronic structure of the surface material, electronic structure in the sense that we can functionalize tip with different type of functional group and we can see their effect in measuring the forces for different type of surface. For example, as we know, carbon nanotube can be metallic or can be semiconductor. Using a suitable functional group, we can differentiate which nanotubes is a semiconducting nanotube and which nanotube is a metallic nanotube, because there is a chemical force of interaction and that depends on the availability of the electrons at the surface and thereby how a particular functional group is behaving on a particular type of surface. In addition to that, as a particular functional group attached to the surface, it can be taken into the sample surface where let us say the protein is there and it can be attached to the protein surface, and we can pull up the protein molecules, that is unfolding the certain type of protein or folding a particular protein in a particular manner. All this can be done with chemical force microscopy. As per the force of adhesion measurement is concerned, there are two models. One is DMT model, also called Derjaguin-Muller-Toporov model, and this model takes into account of Derjaguin approximation, and as per the Derjaguin approximation, which relates the force of adhesion between a flat surface and a spherical tip, or a spherical tip and another also spherical sample. So, it takes into the force of adhesion is taken into account of a flat surface with a spherical tip or both are spherical in nature. Taking those things into account, DMT model provides an equation. The simplified manner we can write that equation as F adhesion DMT model, DMT is equal to 2 pi R W adhesion. Here R is the radius of the tip, W is the work of adhesion, and by measuring the work of adhesion we can measure the force of adhesion. We have other model which is JKR model or Johnson Kendall Roberts model, and that takes into account of a strong adhesive force where a spherical tip makes a strong stress or bonding with the sample surface, and then it is being detached. In that process deformation occurs at the interface, and thus taking more area into account. The force of adhesion as per the JKR model in a simplified form can be written as F adhesion JKR is equal to 3 by 2 pi R W adhesion. Here in both cases R is the tip radius and W adhesion is the work of adhesion. Which is W adhesion is sometimes it is also written as W S T and M, S T M, S for sample, T for tip, M for medium, which is equal to the interfacial energy or surface energy of sample and medium plus interfacial energy of tip and medium minus interfacial energy of sample and tip. So, here these are the surface energy between two medium, surface energy, or in this case interfacial energy, facial energy. One can measure the gamma SM and gamma TM with contact angle measurement also. If in case of same functional group at the tip and the sample, same functional group at tip and sample, then in this case force of adhesion we can write gamma SM is equal to gamma TM and gamma ST is equal to 0. So, by taking this into account we can measure, if we take a single functional group both at the tip and sample, we can measure these values, and thus after measuring this value we can also measure gamma ST. So, all these values can be measured using this equation either in the DMT model or in the JKR model, and the force of adhesion can be calculated with any functional group attached to either tip or the sample. This is about the force of adhesion measurements using chemical force microscopy, and an example as you see, as we attach a particular type of functional group that can be hydrophilic in nature, that can be hydrophobic in nature. In this example that you see here, for example, we can study the functionalities at the sample surface. We can map the pre-patent substrates with particular type of chemicals. For example, in the A that you see where tip is neither hydrophilic nor hydrophobic, as tip has no functionality. Therefore, if the sample is smooth or flat, it will give a one single type of contrast. There is no contrast difference. But even though our sample has both hydrophilic part and hydrophobic part, as sample have both hydrophilic and hydrophobic part, but our tip is non-functional. Therefore, it cannot detect hydrophilic and hydrophobic parts separately, giving a single contrast. But the same sample which has a hydrophilic and hydrophobic components, but if we use a hydrophilic tip, then at the hydrophilic region of the substrate the tip bends. As the tip bends, it gives a signal. So, a different contrast is seen on the sample or beam displacements occur at our detector, thereby differentiating which region is hydrophilic and which region is hydrophobic on the substrates. So, using a functional group attached tip, one can study different functionalities on the surface. Similarly, another example where a hydrophobic tip is taken and hydrophobic tip will bend at the hydrophobic region and thereby giving different contrast. So, it is about just hydrophilic and hydrophobic, but actually we can take any functional group and its bonding with a particular other kind of chemical substrates can be studied. It is just not too restricted with hydrophilic and hydrophobic part, but many other different type of bondings can be studied using the chemical force microscopy. Then we come to magnetic force microscopy. In the magnetic force microscopy, we study the magnetic properties of the sample if the sample is magnetic in nature. So, as we are going to study magnetic properties of the sample, so the tip has to be magnetic. Normally, in conventional AFM measurement, tip is either silicon or silicon nitride. It has no magnetic components. So, in order to study the magnetic sample, the tip has to be magnetic. Thus, a magnetic material should be coated on the tip. So, here AFM with a magnetic tip is used to image the magnetic domains or magnetic component of the sample. So, generally a magnetic film such as nickel, cobalt or iron or some other components of nickel iron alloy or nickel cobalt alloy, these kind of magnetic materials with high coercivity is coated on a AFM tip. After coating that with a AFM tip, it is used to measure the magnetic force generated on the sample. So, in this case there are it is done with a constant height mode little above the sample, because magnetic force is long range order force. Therefore, the tip has to be far away, in the sense here that at least more than 10 nanometer away from the sample surface. If we remember, our contact mode have a less than a gap of 0.5 nanometer, and in the intermediate contact mode we vary the tip distance in the range of around 0.5 to 2 nanometer, and in non contact mode it is above 2 nanometer. So, 2 to 10 nanometer. Now, the magnetic tip is even much away from the sample, that is approximately above 10 nanometer, above the 10 nanometer. So, between 10 nanometer to 100 nanometer a scanning is done above the sample to study the magnetic field of the specimen, and the detection can be the stray magnetic field generated on the sample surface can be detected by many particularly three different process: phase, amplitude and frequency. Phase we have seen, the tip oscillates and the phase shift we measure. Phase shifts can be negative or phase shifts can be positive, depending upon we can know whether attractive or repulsive force. And in addition to that, amplitude variation occurs. We give a drive amplitude and response amplitude is measured, thereby that can be also measured, and frequency modulation can be done. Frequency may shift, the oscillation frequencies can change due to sample and tip interaction. As phase mode is more sensitive and high signal to noise ratio, therefore, most of the time in the magnetic force measurement the phase imaging is taken. And this AFM can be operated in the static and dynamic mode. Static mode involves two measurements. First is that is what called constant height two pass technique. We are saying two pass technique because two times the tip has to scan above the sample on the sample. On the first pass, AFM gives the topographic image, because topography may also be very different on the sample, a different sample. Therefore, a topographic image is taken either in contact or semi contact mode. And after taking a contact topographic image, as you see in the first pass is the the blue color dot lines. Here sample is the tip is scanned on the sample surface with a constant force mode. In this case it is constant force mode, therefore, tip is just following the sample surface, and after taking the first pass, in the second pass tip is retracted to a height greater than 10 nanometer, and then the same path is being followed. After same path is being followed, now in the second pass we measure the magnetic force, because far away from the sample there is no other force that predominates, such as van der Waals force, etc., and magnetic force being long range force can be measured far away from the sample. If we do same thing very close to the sample, then other force will predominate, such as van der Waals force, thereby not giving correct magnetic force information. This is in the static mode. The second pass is done also with following the same path that the first pass followed. In the dynamic technique, which is most commonly used, in the dynamic technique, the first pass is in the semiconductor contact mode. It can be static mode, that means following the surface of the sample with a constant force mode, or it can be also in the oscillation mode. And in the second path, that is always in the oscillation mode. So, in the second pass is recorded at an amplitude above the height h. So, in the second path the oscillation of the tip is made, and then we study the amplitude of the oscillation and frequency of the oscillation, which is due to the stray magnetic field of the sample surface. And in this way we can collect the magnetic field or magnetic region of this specimen, thereby giving the MFM image. In order to do this measurement, here the tip supposed to be magnetized along its tip axis. The magnetic field anyway is depending upon the shape and geometry of the tip. The magnetic field mostly strongest at the tip, and it is in the direction z axis, that is perpendicular to the sample surface. Because of the tip geometry and shape, a very well defined magnetization can be achieved coated with a high coercive magnetic material. We need high coercivity magnetic materials to be coated on the tip surface, because the tip magnetic moment should not be influenced or changed by the sample magnetic field. In case the sample is a strong magnet, or it is a magnetic hard disk, the strong magnetic field of the sample can vary or demagnetize the tip if it has a low coercivity. So, a tip with a high coercivity is required for magnetic force microscopy studies. In addition to that, it should have a low stray magnetic field. If the tip has low stray magnetic field, then it can detect more efficiently the stray magnetic field coming out of the sample. So, in order to have a low stray magnetic field of the tip itself, a small magnetic moment tip is prepared, and in order to have a low magnetic moment tip, the volume of the magnetic volume of the sample at the tip should be as small as possible. So, in this way the tip can detect a small amount of the stray magnetic field of the sample, and thereby giving high resolution and high sensitive image. High resolution in the sense that in case of magnetic force microscopy measurements, the resolution is not as good as that we see in the topography, because here the tip is much above or away from the sample surface. So, here resolution is approximately 10 nanometer, or it can be less than 10 nanometer, but not as good as the topographic image we see approximately less than 1 nanometer or 0.1 nanometer. The tip has to be sharp, that is certainly necessary for having collecting the small amount of the magnetic field from the small region. So, the bottom line is that we have the requirements, the tip should be magnetized along the tip axis, that is z axis, perpendicular. We do not measure here x, y, the magnetic moments of the tip is 0 in the x, y direction, but mostly in the z direction. So, the field also generated in the z direction of the sample is measured in the magnetic force microscopic measurement. and the tip should be well magnetized with high coercive magnetic material, and it should have a low magnetic field, low stray magnetic field, which can be achieved with a low magnetic moments, and that can be obtained with a reduced magnetic volume of the tip, and also it should have a sharp tip. So, these are the requirement to get high resolution MFM image. So, this is an example of MFM image. As you see in the left side, it is a magnetic hard disk. It is almost the contrast difference is almost same, but in the right side image, same sample, you see a specific pattern of the features. These are magnetic bits, and we can see the brightness and darkness contrast. The brightness darkness contrast depends upon the attractive and repulsive force, depending upon how the frequency shifts occurs in the oscillation. If the frequency shift is negative direction, then it is due to attractive force. If the frequency shift is into the positive direction, this is due to repulsive force. So, now we can clearly see the distinction of the contrast in the magnetic by measuring the magnetic field on the sample surface, giving us the MFM image. One sometimes can also do more to it, like for example, one can have another another type of magnetic field, oscillating magnetic field can be applied below the surface of the sample, and then one can do the measurements with a small gap between the tip and sample. In the previous cases, I told that tip has to be far away from the sample, tip has to be far away from the sample, greater than 10 nanometer. In these cases, it can be little closer, and therefore, it is called near field MFM. And in the near field MFM, not only the z direction magnetic moment, some of the x and y direction magnetic moments can also be collected. So, here for this type of sample, this is a magnetic MFM and phase image of a perpendicular magnetic anisotropy material with a ferrite core driven with a different field ranging from 5 austere to 300 austere. So, in these cases, tip material was nickel iron alloy materials, and lift height was above 20 nanometer. The scanning was done in oscillation mode, and driving frequency of the ferrite core was 30 hertz with different driving fields. As we see, as we change the driving field or increase the driving field below the sample, we could see a clear cut contrast difference in the sample. At the low field, it is not clear, neither amplitude image nor phase image, giving us a pattern in their contrast, but as we increase the driving field, then we see the contrast is forming in a particular pattern, which are the magnetic beats. And one important point to note that at a highest field, the maximum contrast difference can be clearly seen, but if we compare the phase and the amplitude mode, in this case phase is giving a 180 degree signal difference. This is one color and this is yellow color, that is different color contrast difference. But if we see in the amplitude cases here, then we see the strongest signal, certainly the brightest signal is recorded with the beats, and around the beats we have a completely dark boundary, which is not appeared in the phase image. Dark boundary is not appeared phase image. Dark boundary is due to your attractive force. There is almost zero magnetic moments. That is a different type of magnetic moments at the boundary of these magnetic beats, which is not observed in the phase image. So, by varying the magnetic field etc., one can also do further studies with magnetic samples, as that you see here. Then we come to another force microscopy, that is called Kelvin force microscopy. So, it works with a conventional Kelvin probe methodology or the principle. Here this is used for to measure or map the surface potential in a non-contact. This is a non-contact version of AFM, where work function is measured in atomic and molecular scale, and by measuring the work function and the field, we can know the difference in the electronic structure at the surface. So, here tip oscillates. Here one of the important things that Kelvin probe microscopy, the tip has to be conductive. Tip has to be conductive, and it has to oscillate above the surface of the above the sample, and thus and then when it oscillates above the sample surface, it changes. This is like two electrode in a parallel plate capacitor. Here one is sample and one is tip, that is the two electrodes acting as a parallel plate capacitor. As we change the tip sample distance away or we vary, then what we will change the capacitance, we will keep on changing the capacitance, and thereby we will also change the displacement current between them, and what you see, if you look at the working principle, if the tip and sample are two different materials, and once they come close to each other, then electrons will flow from higher Fermi level to the lower Fermi level, and thereby creating a surface charge at the interface between the sample and tip to maintain the same electron flow electrons energy diagram, energy with same level of diagram, and thereby creating a potential difference because of the charge creation at the interface. A potential difference is created between the tip and sample, and that potential difference is called contact potential. And when tip is oscillated above the sample or thereby modulating the gap, a displacement current is generated, and which can be converted to DC signal with a lock-in amplifier. And then in order to make this displacement current to 0 or to nullify the displacement current, we can apply a bias potential. We can apply a bias potential, or that is called backing potential. So, by applying a backing potential, we can nullify the charge or nothing but driving the current to 0, and how much the backing potential, that is nothing but the contact potential or potential difference between the tip and sample. If we know the work function of the tip, then we can measure the work function of the sample, because work function is the difference between the Fermi level and the vacuum levels. So, in this way work function can be measured and surface potential can be measured of the sample. It is an example being shown here. So, here is a atomic force microscopic image and Kelvin force microscopic image of graphene. In the left one, here what you see, there is a contrast difference that indicates the height difference, and that height difference may be due to same material or may be due to different material. In this particular cases, atomic force microscope cannot tell it is due to the same material or different material. It will just say it is a height difference. And for example, by measuring this height difference here or measuring this high resolution image here, that is being found 0.07 nanometer, and this do not reflect with one single layer of graphene. This is smaller than one single layer of graphene. So, it cannot be told that this is a two layer graphene, this is one layer of graphene. So, height measurements cannot be sufficient, but if we do a Kelvin force microscope or surface potential measurement, we see a contrast difference. So, as there is a contrast difference, that clearly say the electrical properties of this region and other region are different. So, thereby confirming that these are two different kind of materials, and particularly in this case it is a two layer graphene and one layer of graphene. And in addition to that, as this does not match with the thickness of one layer of graphene, that means there is a non-uniformity where they placed on the surface of the substrate. In here substrate is a underlying substrate is a silicon carbide, and silicon carbide steps are not even, and as you see this is 0.7, the thickness of the graphene is around 0.33 nanometer, which is almost 4 times smaller than this. That is why in this side there is a two layer of graphene with a different surface potential. In the left side there is a one layer of graphene with a different surface potential. This can be confirmed by Kelvin force microscopy, which cannot be obtained from the simple topography of the AFM. So, same sample as you see in the topography, in the left side topography image. In the topography image we see some contrast difference, but for example, in this region where the arrow is given, that do not give us any topography difference, that is because there is no height difference. But in the Kelvin force microscopy, the same region you see complete contrast difference, indicating that in this region there is actually two different materials is present. and that contrast difference is due to the electrical properties of the sample surface, which can only be achieved with Kelvin force microscope, or that is called contact potential map measurements. So, in the Kelvin force microscopy, the difference in contrast is due to the electrical properties, varying electrical properties, and varying electrical properties is due to the inhomogeneity in the sample, or sample have different type of materials, thereby giving different type of electrical properties. Another microscopy is the conductive AFM. Here, as the name suggests, conductive. So, the tip has to be certainly conducting, and when a conductive tip is brought close to the sample surface, then we can also study the electrical properties of the sample. So, it works in the contact mode operation. In the contact mode operation, tip is brought close to the sample and kept at one location, and after keeping at one location, you can vary the potential, and measure the current, and thereby measuring the IV characteristic at single point, Otherwise, what you can do, you can scan the tip over the region of interest under a constant voltage and measure the current. So, thereby knowing at which places current is more, which current is less, thereby telling the conductivity mapping on the surface of the sample, and how conducting in some region, how much more conducting in some region, how much less conducting in this other region. So, this can also be done with a conductive AFM, and as we measure IV characteristic, see this IV characteristic can also be used for measuring the mobility etc. As per the Mott-Gurney law, there is a relation J is equal to 9 by 8 and epsilon naught and epsilon mu is the charge mobility, V square by dq. So, here V is the voltage given, and T is the thickness of the active layer, on the surface, and mu is the mobility, and epsilon 0 is the permittivity of the free space, and epsilon is the dielectric constant of the material. So, by using these factors and J we measure the current, voltage we given, we can get the, and thickness we know, we can get the mobility of the charge carrier mobility of the sample surface. So, this can be measured with a conductive AFM. And this is also primarily done, also can be used for measuring the electrical properties of the dielectrics in the semiconductor industry. Dielectric films on the semiconductor surface can be measured by putting the conductive tip on the surface and measuring their current voltage characteristic. And this can also be used for measuring electrical properties of any nanomaterials, including 1D materials, 2D materials, by touching, if it is a, let us say it is a 1D material, 1D materials is like a pillar or wires on the surface of a material. Now, AFM tip can touch over this, can contact at the tip of this nanorod, and here is a conductive surface. We can take, we can give a potential difference between these two, and then measure the current, and by measuring the current, we can plot IV characteristic, and thereby measuring the electrical characteristic of single nanorod or single nanotube. All these can be measured by conductive AFM. Example here, another is shown here how the conductive AFM mapping is done. Here is the topography image A, B, and the topographic image of cadmium telluride and cadmium sulphide, and after this, this is 1, 2 are the two untreated sample, and C, D are the treated sample, which are cleaned by bromine methanol etchant solution at different concentration. This A, B are the sample, different A, B are the topography image, and the C, D is the current mapping. And what we could see at the interface of the grains, it is more brighter. This indicates there is a more current is flowing at the interface. It suggests that the grain boundary after etchant, grain boundaries become more conducting, and if in the I versus in the plot of current versus distance, we could see at the much current, higher current at the grain boundaries, indicating that grain boundary change its properties after it being etched by a bromine methanol solution. So, this type of measurements can be done using conductive AFM, complete electrical properties of the surface. So, in conclusion, what we have seen that using chemical force microscopy, chemical identification, adhesion force can be measured. In addition to that, high resolution non-contact mode topography can be taken. MFF magnetic force microscopy measurements is used to study magnetic materials, and Kelvin force force microscopy is used for work function and surface potential measurements of the sample using a conductive tip. Conductive AFM again is used for measuring the electrical properties, particularly IV characteristic of any type of conducting sample. These are the references, and thank you.